Hey everyone, thanks so much for watching. My name's Jason, and I'm very excited to be telling you about our work on learning Markov random fields from dynamics. And this is based on work with Ankur and Elkinen also at MIT. So the game plan for the talk is first, I'll tell you a bit about what Markov random fields are and prior work on learning them. And then I'll tell you a bit about our new results. And then in the second half of the talk, I'll tell you a bit more about some of the technical ideas that go into our algorithm. So let's get started. So a central goal in statistics and machine learning is you often want to infer latent system structure. So for instance, like network interactions from observations or data. And so a very principal class of distributions that people have studied is something called Markov random fields. And what these are structured distributions that you can think of on being plus minus one spin configurations. And they have local dependencies. And these models are studied across economics, so for instance, in networks applications, statistics like in machine learning and computational biology and physics and so on. And so an example of this coming from the physics community is something called the Ising model, which is defined as follows. The probability that the random variable x takes a certain value is going to be proportional to e to this quadratic term over here, so sum of aij, xi, xj, which encodes the pairwise local interactions between spin values, plus this term sum hi, xi, which corresponds to each site's individual external field. And then to make this a distribution, of course, you should divide everything by some normalizing constant, and this is often called the partition function. So more generally, a Markov random field can be defined as follows. So we'll say a Markov random field mu, which is going to be parameterized by a function psi, is going to be a distribution on plus minus one to the n, where the probability that x takes a certain value is going to be proportional to, again, to e to some psi of x, where psi is going to be a degree k multilinear polynomial. And so if it's a degree k polynomial, we're going to say the Markov random field is order k. So for instance, in the Ising model, this is going to be a order 2 Markov random field. And so what you get by expressing these higher order Markov random fields is that you often get richer structure. For instance, the higher you take the degree k, you can model richer structure like communities and networks. Or even if you were just interested in the Ising model, like for in the physics applications, you would get these kind of higher order models if you try to marginalize out variables. And so for each Markov random field, an important object that we'll come back to in just a sec is the so-called dependency graph. And that's a graph G on the n variables, x1 through xn, and we're going to put an edge between variables, xi and xj, if xi and xj have direct interactions in the polynomial psi. In particular, that'll mean that the mixed partial derivative, partial I, partial j, is not always zero. Another way to think about it is that I and j both belong to some monomial that's non-zero in the polynomial. And so the main question we're going to be considering this talk is the following. When can we efficiently learn Markov random fields, mu of psi, from data? And this is a question that's been studied for several decades in the statistics, machine learning, and computer science communities. So what do I mean by learn the Markov random field? There's a couple different objectives you might have. The first one is something called structure learning. So for instance, you might want to know which variables directly influence each other. So what that means in the language I just introduced is, can we recover the dependency graph G? More ambitiously, you can hope for something called parameter learning, which means you actually recover the coefficients of the polynomial psi up to some given epsilon accuracy. And so, as I said, this has kind of been a well-studied problem in many communities, dating back at least to the work of Chow and Liu from 1968. But from the computer science perspective, the first efficient algorithm, at least for the Ising model that I introduced earlier, was given by Bressler around a decade ago. And for these more general higher order Markov random fields, these results were improved and extended by Clivens and Mecca and then some other works a couple years later. So let me tell you a little bit more about what we know about these models. But first things first, kind of just to set some notation for the rest of the talk, let me give you a couple key parameters. So we're going to associate a few parameters to the Markov random field. The first is we're going to say the Markov random field, as I said, is order k, if that polynomial psi is degree at most k. We're also going to say it's d-sparse if that conditional dependency graph I mentioned has graph theoretic degree at most d. So that means is each variable is influenced directly by only at most d other variables. And then, of course, if I want to detect whether two variables actually influence each other, I'm going to need some sort of non-degeneracy condition to distinguish between the case they don't actually directly interact or it's a very weak interaction. So we're going to make some alpha non-degeneracy condition, which says that if I and j directly interact, so they're an edge in the dependency graph, then there is a maximal monomial of psi that contains xi, xj, whose coefficient is at least alpha in magnitude. And this just ensures that there's some monomial that kind of certifies that they non-trivially interact with each other. The final condition is something called the lambda width condition, which says that each variable, if I take all of the coefficients in psi and sum up the absolute values of the ones containing a given variable xi, then it's at most some parameter lambda. And this basically just says that no spin can get too conditionally biased given the rest of the variables. And all of these kind of conditions are standard in the literature, and they're more or less necessary if you want to give any sort of kind of good algorithmic guarantees. So what have people come up with for this learning problem? So the standard setup is that you get IID random samples, and then you want to just do either of those learning tasks I mentioned. So for the case of structure learning, the Klivans and Mecca result says the following. Suppose I'm given these IID samples x1 through xp drawn from mu of psi, and let's assume it's some non-degenerate MRF, let's say it's order k, and it has lambda width. Then, so long as the number of samples p is at least this parameter here, which is something like e to the lambda k, then just times log n, so the number of spins, then there is an algorithm that can actually recover the structure, so the dependency graph G, and the runtime of the algorithm is going to be O of P, the number of samples, and then times N to the K. Now, for the setting of parameter learning, again, Klivans and Mecca show that if I want to further actually recover the coefficients, let's say to some constant tolerance, then now I need the number of samples to be, again, E to the lambda K times now N to the O of K instead of logarithmic. And the runtime is, again, going to be something like the number of samples times N to the K. And these are kind of the state-of-the-art guarantees that we have for this learning problem. So how should we think about these? So it turns out that the sample complexity for structure learning that I mentioned above, which had this log and dependence and this exponential and lambda and k, this actually turns out to be provably near optimal by some results of the last decade. But as I mentioned before, the runtime is actually n to the k or worse. And so what about that? Is that actually necessary, or what's going on there? And it turns out that actually these higher order Markov random fields, they're very expressive. And in particular, if I only have a single non-zero term of an order k plus 1 Markov random field, you can encode something called the k-sparse parity with noise problem. And all that is in this setting is you just set psi of x to be the parity of the variables in a subset S, or SS size k plus 1. And this turns out to be a very big issue because actually the sparse parity with noise problem is actually kind of a fundamental computational barrier across several domains. So for instance, in learning theory, it's kind of a barrier to any sort of efficient learning. And actually sometimes it's used as kind of a cryptographic primitive. And the point of this problem is that it's actually widely believed to require something like n to the theta k time. Again, even for this case where I know that the MRF is extremely sparse. And this is actually believed to be unimprovable. It's not just kind of our lack of algorithmic ingenuity. So, okay, it sounds like the problem is kind of completely resolved. We have these upper and lower bounds, and it's kind of n to the k runtime blow up. And it seems like that's kind of all there is to say. But actually, let me try and give a change of perspective. And the question I want to ask is actually, why did we make the IID assumption in the first place? So again, the setup of these all prior results were that, I get these samples x1 through xp that are drawn IID from the distribution, and then I have to kind of try and do the learning problem. But what kind of data do you actually expect to get in practice? Well, in real world applications, we think of data as coming from nature. And in particular, we think nature is kind of evolving according to some sort of physical process. And that's the kind of thing that gives us actual observations that we hope are clean samples to kind of reason about in the classic statistics setup. But it turns out that sampling from these higher order Markov random fields, or even from the Ising model, can be provably hard in the regimes that these learning guarantees cover when there are so-called long-run correlations. And these are by some seminal results of Sly and Son. And in particular, we don't expect any to be able to sample from them, and we shouldn't expect any efficient process to yield clean samples, let alone coming from nature. So actually, the question we want to pose in this work is, can we actually design provably better learning algorithms for learning Markov random fields that overcome these kinds of inherent computational barriers, but do so by directly working with somehow more realistic models of data? In other words, we made these IID assumptions because it's very classical and standard in statistics and CS and so on, but were we losing something by it? And can we actually get better results by assuming the kind of data we should actually expect to observe in practice? So to do this, let me introduce a kind of natural model of dynamics that have been studied across a variety of fields, and that's something called the Glauber dynamics. And in particular, our work is going to aim to learn Markov random fields, but instead of observing these IID samples, we will observe a short trajectory of the so-called Glauber dynamics. And so the Glauber dynamics, as I said, are well studied across several fields, often going by different names. So in economics or networks applications, it's called noisy best response dynamics. In physics, it's sometimes called the heat bath dynamics. And of course, many people in the computer science community will know it as kind of a nice sampling algorithm, so MCMC. And I just want to note that this model of learning from Glauber dynamics was actually introduced around a decade ago by Bressler, Gamarnik, and Shaw for the Ising model. And in particular, their work shows how you can kind of give a different algorithm, but that more or less gets the same computational and statistical guarantees as we know for the Ising model when I'm given IID samples. So what are the Glauber dynamics? They work as follows, and they're well defined, no matter how hard it is to sample from the true distribution. So you do the following. You start with any configuration x0 and plus minus 1 to the n, and let's say the gray spins here are plus 1, and the white spins here are minus 1s, and then I've drawn the dependency graph of the MRF. And what's going to happen is each variable is going to independently have a clock associated to it that rings according to exponential random variables at rate 1 in continuous time. And so what happens is when a spin tries to update, they'll do the following. If they try and update at a time t, then given what's happened so far and what the current configuration is, we're going to resample its value according to the conditional distribution of the Markov random field, but given the outside configuration. So in other words, the probability that the spin will try and update to some epsilon and plus minus 1, given the rest of them, is going to be proportional to e to the spin value times the partial derivative for it of psi. And this is kind of its part of the Hamiltonian. And so what it'll do is, again, it'll kind of look at the outside configuration, but kind of by construction, you only care about your graph theoretic neighbors in the potential function. So it'll look at its neighbors in green here, and then it'll decide, does it want to update its spin value? And then the next spin will decide what to do. It'll again try and update its value. It'll look at its neighbors, and then it'll decide whether to switch or not. And we can continue this so on and so forth. And we're going to make the following assumption, as in the prior work, which is that we observe all the updates, not just ones that cause a flip. And I'll come back to this at the very end. So our main result for structure learning is the following. So suppose that we have an order k, d sparse, and alpha non-degenerate MRF with this width at most lambda. So all those parameters I gave before. Now suppose we observe a trajectory of Glauber dynamics for this Markov random field that's run for time t, which is some function of d, k, lambda, and alpha, all these parameters, but times log n. And when I say this, I mean in continuous time, so each spin updates at rate 1, so the total number of updates should be n times t, basically. Then our main result is that there's a structure learning algorithm that now just has runtime O of t times n squared. So in particular, this is something like n squared log n. And that will succeed with high probability in recovering the dependency graph. And I've written the actual dependencies on the other parameters below, but I just want to mention they're kind of qualitatively more or less the same as you get for the IID setting for these parameters. And the main point is that we kind of replace all these n to the k time dependencies with just like an n squared. And so the main takeaway from this result is that dynamics seem to not only give a conceptually better generative model for the kinds of observations you'll observe, but they actually are also overcoming the computational barriers for IID observations that I mentioned before with this sparse parity with noise problem. On the parameter learning side, we have similar results, which is that, again, suppose I have an order k d-sparse MRF with at most lambda, and now let's suppose I know the dependency graph G. Then kind of given any accuracy parameter epsilon that I want, and now again, suppose I observe a trajectory of Glauber dynamics that's now run for something like O tilde of log n time, again, with some constants that depend on the other parameters. Then there's an epsilon parameter learning algorithm whose runtime is now just n times poly t. So again, we're completely kind of getting past all this n to the k type sample complexity or runtime for this problem. And again, I just want to note that because of the previous result, we can actually just assume access to G if you just run the previous structure learning algorithm I mentioned in the previous slide. And again, the takeaway is that dynamics are not just a more natural model, but they also help overcome these fundamental computational barriers that were leading to these computational statistical gaps. So in the remaining part of the talk, I just want to tell you a bit about some of the technical ideas that go into the structure learning algorithm. And then for the main stuff on the parameter learning, I'll kind of leave it to the main paper. So for structure learning, the fundamental task we have to do is we have to decide the following. Is xi kind of connected to xj in the graph? And we need to be able to answer this for any pair I and j. And so we can use the following heuristic that actually comes from this previous work of Bressler, Gramarnik, and Shaw that I mentioned, which is to try and kind of isolate the effects of I and j onto each other using dynamics. And the way we can try to do this, at least in the Ising case, is as follows. Suppose we observe the following sequence of events in a short window, kind of back to back. Suppose we first see that I updates to some value, let's call it y1, in this Glauber dynamics. And then suppose that very closely after j then updates and actually flips its sign. And now suppose that I again tries to update very close by, and now it updates to some value y2. And what we should try and test now is there some sort of statistical difference that we can determine between the case that xi was actually directly influenced by xj and the case that it's not directly influenced in xj. And can we do so using these random variables y1 and y2? And we can do so if there's some kind of statistical difference that we can kind of isolate and understand. And so in the Ising model, the heuristic that they use is as follows. Okay, first let's suppose that there's no interaction between them. So in terms of that Ising model I mentioned above, in these quadratic interactions, the cross term is aij xi xj, and suppose that it's actually just zero. So there's no direct interaction between them. In that case, when I do this intermediate change of j from whatever it started with to the other value, this has no effect on how xi is updating in the dynamics because they're not directly influencing each other in the potential. So in particular, if I take the expected value of y1 minus y2, I'll just get zero because both y1 and y2 just have the same conditional law, no matter what j was, given everything else. Okay, but what about the other case? Suppose now that aij is non-zero because I and j interact with each other. And under this non-degeneracy condition, we can assume that it's at least some parameter alpha in magnitude. Then is there some sort of statistical difference we can test? So let's think about the following. Suppose, just for simplicity, that xj was initially +1 before I saw any of these events. Then I should actually expect different laws for y1 and y2. So for y1, the probability to equal some value epsilon when I do the Glauber update before xj changes, it should be something like e to the epsilon times c plus aij, where c is just the contribution of all the other spins, which has a most lambda in magnitude. But it's going to be plus aij just because xj is initially +1. But when xj moves to -1 and I now evaluate what's the conditional distribution of y2, I should now get a minus sign in front just because the part with xj has now changed. And in particular, the observation of Bressler, Marnick, and Shaw was that if I now just, okay, if I just have to change kind of the sign of the statistic, but there should be kind of a consistent way to say that the expected value of y1 minus y2 is far from 1. And it'll depend a little bit on kind of what alpha is and what lambda are, but the fundamental observation is that y1 and y2 have kind of an easy to understand difference when they are in fact connected to each other, and we can actually easily detect for this. And so in particular, their algorithm runs something like this, which to recover G, what we should do is we should take the statistic y1 minus y2 when we observe this event of iji flipping. And then we should, aggregate this over log n such events, and then use some sort of concentration bounds to say that there's a difference between the case that they're connected and the case that they're not. And now one thing I should mention is kind of the way I've described it, we asked for this event to happen in very short succession. Kind of naively, this will take something like n to the cubed observations to observe this iji pattern. But it turns out that, you can actually kind of reduce it to n log n observations if you pay a constant that depends kind of on the sparsity and these other parameters just by setting the window size appropriately. And that's kind of the algorithm for what you can do in the Ising case. So now one thing we need to ask is this argument, did I cheat you anywhere? And also, does it generalize to higher K? And so the main challenges are as follows when we try and kind of make this argument work in general, which is, okay, issue one was, did I actually write down the correct distributions for y1 and y2? And the subtlety is that even though the distribution of y2 was correct, because we defined this event by conditioning on xj flipping, we've actually changed the law of the first update, y1, even though it happened first, kind of counterintuitively. The other issue when we try and generalize this to higher order models is that we have a very clear understanding of how j locally affects I, no matter what the rest of the configuration looks like. And that's because aij, like, no matter what else is happening, we know that the magnitude of this is at least alpha under this non-degeneracy. But for higher order MRFs, the local effect between I and j is now just going to be a random variable. It's going to be this mixed partial I, partial j of the Hamiltonian evaluated on the other spins other than I and j at that given time. So in particular, it could just be close to 0, even if they actually are neighbors a lot of the time. So that's something we have to account for. But the biggest issue is that actually for higher order MRFs, the issue is that this mixed partial derivative that gives the local effect changes sign. So in particular, even if they are neighbors, there's no longer a consistent effect. Whereas in the Ising model, aij kind of tells you whether I and j locally want to align spins or if they want to mismatch spins. For higher order MRFs, this is not true. And in fact, this is actually a big problem because what you can show is that there actually are examples where if I kind of abstract this sampling model that we're using for Glauber dynamics, if I kind of define a very idealized version of it, there's actually no statistical tests that could just use these samples of the form y1, y2 in kind of the way I've defined it before that can determine whether or not I and j are connected for MRFs, even once I get to order 3. So for the Ising model, which is order 2, and that's what Bressler, Marnick, and Shaw studied, it works. But for order 3 and higher, it actually turns out to be information theoretically impossible. And the reason is that you can just find 2 MRFs where the law of y1 and y2, where I kind of average over the rest of the configuration, it's going to be identical in both models. However, in only one of the models will I and j actually be connected to each other. So we're going to need to kind of change this model, but as we'll see, actually the intuition though is still pretty good, which is to try and localize their effects on each other. So let me give you some intuition for the algorithm. And in particular, our solution to this issue is we're just going to try and just take a couple more conditional samples on each side of this j update. So the new event that we're going to define is the following. So again, we're going to wait for a short window of time where the following occurs. First, we're going to observe at least two attempts for I to update, and let's call this y1 and y2. So I'm changing the definition a little bit. And then we're going to see j attempt to update, but we're not going to condition on it flipping because, as we said, there's kind of an issue there. And now we're going to see two more I updates, which we'll call y1 prime and y2 prime. So we're looking for kind of a configuration of updates that looks like I instead of IJI. And then the test statistic we're going to define is just now this kind of weird looking quadratic term, which is going to be y1, y2 minus 2y1, y1 prime plus y1 prime, y2 prime. So where does this come from? Well, first of all, let me just say, as I said before, y1 and y2 alone are not are in the way I defined it before. So here, y1, y1 prime is not good enough to determine I and j by these lower bounds. So in some sense, this is actually the smallest possible statistic you can use because we're just kind of taking one extra conditional sample on each side. And so, okay, how does this work and why should we think this is a good thing to do? So again, let's suppose that xj is initially plus one. And then again, kind of the same heuristic reasoning is that we now expect the conditional law of y1 and y2 when they're sampled to be the same thing. They're going to be IID, and the law is going to be like e to the epsilon times, the stuff that comes from the rest of the configuration, and then plus this mixed partial. And then if it is the case that xj flipped to -1, again, we're not going to actually condition on it, but if it did happen, then we'd expect the conditional law of y1 prime and y2 prime, so the updates afterwards, to again be IID with this law, but now the contribution from j is now flipped to a minus. So again, we should hope that there's some kind of difference there. So what's going on and why does this help? So again, the same heuristic though is that if I didn't have this issue about conditioning on a flip by the j in the middle, and if it's the case that this effect actually is noticeably far from zero, then I should expect that the magnitude of the expected value of y1 and the expected value of y1 prime to be different, far from zero. I don't know what the sign is again, but I at least expect them to be different. And then we can actually bootstrap this using the z statistic by, if I just take the square of this quantity, I should expect that, the square is still at least like a constant, and then I can expand it out. So I get just the expected values. I've just written it out with the cross terms. And now I'm going to replace the y1 with y2 now, because we said that they were the same law, and same with y2 prime. And now I'm going to kind of claim using this conditional independence that I can actually push these two guys back in, and same with these guys. And then, just linearity of expectation tells me this is the expected value of z. So if I and j actually are neighbors, then I expect that kind of z should reveal this. And if I do all this kind of reasoning, but I and j are not neighbors, you can actually just show it zero. So this is kind of the intuition behind the statistic, but why is this kind of getting over the issues I mentioned before? So it avoided issue 3, the sign issue, because as I said, we just kind of squared the statistic. So we didn't actually care whether y1 and y1 prime, how they related. We're just squaring it to kind of fix the sign ambiguity. But why is it kind of getting around the correlation issue, this fact about conditioning on the middle? So the kind of key observation that underlies our analysis is that the only correlation really that you have to worry about comes from the cross term here, y1 and y1 prime, because there's kind of a j sandwich between them. But it actually turns out these are independent, even conditioned on the value of whether j flipped or not. And the reason for that is that kind of this intermediate sampling of xj, it only ever observed the second or later initial updates of xi. In other words, it never actually sees the how xi updated in terms of y1. So there's actually ends up being no way for for y1 to actually influence what happens with y1 prime. And to kind of make everything work, of course, you have to condition carefully, and then also, as in what I alluded to earlier, you have to kind of account for the low probability event, some other neighbor of I updates. But again, this can kind of be dealt with by setting the window size that I measure these events on kind of sufficiently small. So the second issue I just want to mention is, again, in the Ising case, we kind of knew that the effect is always like at least a constant. Here, this is just like a polynomial, and it could be close to zero with non-negligible probability. So our solution here is you need to use some sort of anti-concentration result. And in particular, this is a low degree polynomial, so we're looking for an anti-concentration of that kind. And so kind of a technical lemma we use to show this is the following, which says, suppose I have a distribution on plus minus one that I can obtain by kind of sampling a random permutation of the variables. And then I sample according to what's called a Santa-Vazirani source, which means I sample in that order. And every time I sample, conditioned on whatever happened before, I have some kind of lower bounded variance for each setting of the next variable. It turns out then that if I have such a distribution, then for any degree k polynomial and any maximal monomial z of s in it, the probability that f exceeds the magnitude of that coefficient will have some lower bound depending just on d and the degree k. And so we kind of use this fact to argue that we can apply this for the mixed partial derivatives that we care about to ensure that enough of the time the effect of I and j is noticeable for the statistic to kind of capture. And that's kind of how we get around this second issue. And kind of combined, this statistic will give us our structure learning algorithm that's kind of bypassing these kind of barriers that come from the sparse parity with noise problem because we are able to use dynamics to isolate local effects of each other. So in conclusion, I just want to mention again that for the setting of Markov random fields, it seems that learning from temporally correlated data is actually attaining a sweet spot of realism in terms of the model we use of our data, but also in terms of getting better algorithms that we could ever hope for from kind of the classical IID setting. So just to leave you with a few open questions, the first question is, can we actually learn from dynamics in this model if we have somewhat coarser snapshots? So to run this algorithm, we need to be able to kind of see the configuration of very kind of granular scales. And it'd be interesting if we could kind of come up with a similar algorithm that could succeed in structure and parameter learning that doesn't have to kind of observe the dynamics all the time. I mentioned this assumption earlier, but this algorithm kind of uses the assumption that we observe all updates, even if an update doesn't actually result in a flip. And kind of the most natural form of learning from dynamics would show that you just kind of observe the configuration as it evolves. And if something doesn't change when it tries to update, then you wouldn't see it. So it turns out that we can show that this is possible for the Ising model, but doing this for the higher order case, and in particular doing this and getting all these computational benefits is still open. And then, but more generally, I think the question that's very interesting is, where else can these kinds of dynamical forms of data improve algorithmic guarantees for these kinds of statistical problems beyond what we know is possible in the IID case? With that, thanks so much for paying attention.